Okay, let's look at factorizing via completing the square. Now, in the topic of quadratics, this will help get you your quadratic equation into the turning point form, where your h and k values would represent the turning point coordinates. Now, how does completing the square work? So, again, this should just be a revision. You should have seen this in your year 10 content and in this topic in your class already. But let's say you have um, x plus half b on this side and x plus half b over here. So if this length is x plus half b and this length is x plus half b, we get the area of this square by multiplying together. So we would have x times by x would give us an x squared component. X times by half b would give us a half bx. Again, x times by half b would give us a half bx. And then half b times by half b would give us a half b all squared term. Now combining these, so you have an x squared plus, so a half b plus a half b gives you two lots of half b. So you have a full bx plus a half b squared term. So this is the expansion via completing the square. Now, if you have, let's say you have ax squared plus bx plus c. You've got your quadratic equation. Now, let a equal 1. Otherwise, this gets a little bit complicated. So we have x squared plus bx plus c. If I want to factorize this in the most generic way, I can say, okay, these first two terms, regardless of what C is, these first two terms are very similar to this x plus bx expansion. So if I had a half b squared term, I could factorize these first two. So what I'm going to do is I add this in, but I can't just add something because then you're changing its value. So if you add something, you have to subtract it as well. That way you're changing its representation without changing its value. We go x squared plus bx plus half b squared minus a half b squared plus c. So I've added and subtracted this term to the generic equation. These first three terms now match the expansion of x plus a half b times by x plus a half b. So it matches the form x plus a half b all squared. So these first three terms simplify to x plus half b all squared. And then because these two terms are independent of any x value, they're just numbers. So they're going to combine. We don't know what they are in this case because they're letters, but they will just combine to half b squared plus c. And so if we look at the structure, we have one set of brackets that's squared, and then you're plussing effectively a number. And now if we look at our turning point formula, we have one set of brackets squared plus a number. And so taking a quadratic equation, regardless of what structure it is, like in terms of the numbers and the coefficients included in this quadratic, we can factorize it via completing the square into the turning point formula. So let's go over a few examples just to try and make this a little bit clearer, as just talking about this in letters can make it more confusing than it needs to be. But it's worth seeing the proof behind this. Okay, so let's look at this question or this equation that we looked at in the previous video, x squared plus 5x plus 6. When factorizing it via the decomposition method, we can get it into a completely factorized form, which is useful for finding the x-intercepts when you apply it via the null factor law. So we'll get into that a little bit later, but it's got its uses. Now, we could also factorize this via completing the square. So let's look at this equation. Now, in completing the square form, we need to know what the b value is. We need to know what the half b value is. And we need to know what the half b squared value is. So our b is our 5. So half b will be 5 on 2. And half b squared will be 5 on 2 all squared, which is 25 on 4. So you square both the numerator and denominator. Now, in this example, we were adding and subtracting a half b squared term to our equation. So we're adding and subtracting this term to our equation. We have x squared plus 5x plus 25 on 4 minus 25 on 4 plus 6. So we still have the original 3 terms, but then we also have this plus and minus 25 on 4. So these first 3 terms, the definition says that this should simplify to x plus half b. So x plus 5 on 2 all squared. And then we simplify these 2 terms. The minus 25 on 4 plus 6. Now, I'm just going to prove that this expands into this, or this factorizes into this. So before we move on with the question, let's just prove that this is true. So we had x plus 5 on 2 all squared. X plus 5 on 2. X plus 5 on 2, because it's squared. So x squared plus 5x on 2 plus 5x on 2 plus 25 on 4. So we have x squared plus 10x on 2 plus 25 on 4, and 10 on 2 simplifies to 5. So this simplifies to x squared 5x plus 25 on 4. So x squared plus 5x plus 25 on 4. So this does simplify to this, and we can fast track it instead of having to do all the math. We can fast track it by just applying knowledge about how to use the half b squareds, the half b's, and the b values within the equations. So we'll go over a couple more questions like this, but let's finish this one off. So we want to combine these together. So 25 on 4 plus 6. To combine these, they have to have a common denominator. So 6 would scale up. So you'd multiply it by 4 on 4 because 4 on 4 is 1. So you'd scale this up to 24 on 4. We're 25 on 4. So negative 25 on 4 plus positive 24 on 4 gives us a quarter. X plus 5 on 2 squared, negative a quarter. And that would be the end answer for that question. Now, if we were to plot this, we would see that it would have a turning point of 5 on 2 and a quarter. Seeing as your turning point form has a negative in the equation, we want to represent the symbol between the x and the h as negative, so we can actually see what that h value is, and then we want to use a positive there. So let's just restructure this to get it very similar. So we have x minus 5 on 2. And then we want a plus negative a quarter. So now it's of the form x minus h squared plus k. So you got that x minus h, so h is negative 512, plus k. So k is negative a quarter in this case. And so we would have a set of coordinates for the turning point being negative 512, comma, negative a quarter. So I'll just write this on a new page. Okay, so if this equation was equal to y, via completing the square, it puts it into the turning point form, which would give us the turning point location. And via the decomposition method or the Australian decomposition method, it would give us the uh, x-intercepts. So you would use the null factor law to find that. So as in, if seeing as these are multiplied together, if this is equal to 0, the whole thing's equal to 0, and so y is equal to 0. Or if this one's equal to 0, again, the whole thing's equal to 0 and y is equal to 0. So you could have when x plus 2 is equal to 0, or when you have x plus 3 is equal to 0, these tell us that rearranging, so x is equal to negative 2, and x is equal to negative 3, it says that the x-intercepts are negative 2 and negative 3. And back in the original equation, if you let x equal to 0, you see the y-intercept is 6. So x equal to 0, the y-intercept is equal to 6. And so each structure of the same equation tells us something different when you're trying to plot this kind of graph. So if I just jump over to Desmos and I'll pull this equation up, and we'll see what the turning point is, and we'll see what the x-intercepts are and what the y-intercept is. Okay, so I've just typed in the equation into Desmos, and we can see what the graph would look like. Now, we see that the y-axis is crossed at y is equal to 6 when x is equal to 0. We can see that the turning point is negative 2.5, negative 0.25, so negative 512 and negative a quarter. And we see that the x-intercepts are negative 3 and negative 2. So again, all the details that we found from the three equations. Before we move on to a question for you to practice, I'll just show that we could actually still factorize it from this method into a completely factorized form by then using the a plus b, a minus b technique. So previously we have seen that when you multiply a plus b by a minus b, you end up with a squared minus b squared. So this is effectively, so I'll rewrite this, but not in the turning point form. I'm going to combine this plus and this minus to make it a minus a quarter. So we had x plus 5 on 2. So I brought it back, combine these two minuses as well. So we had x plus 5 on 2 squared minus a quarter. So if we effectively treat this as this is our first term squared, this is our second term squared, then we can bring it into this form. So our first term, a, is the square root of all of this. So the square will just disappear. We have x plus 5 on 2. And we're plussing b. So b squared is a quarter. So if b squared is equal to a quarter, then b is equal to the square root of a quarter, which is equal to a half. So you apply the square root to both to the numerator and denominator separately to make it easier to figure out that it's equal to a half. So you can have x plus 5 on 2 plus a half, and then we have x plus 5 on 2 minus a half. So that's our a plus b, a minus b. So we have 5 on 2 plus a half. That makes it 6 on 2 because they already got a common denominator. So you have 6 on 2. So x plus 6 on 2 and x plus 4 on 2. 5 minus 1. Then simplifying this, 6 on 2 is 3 and 4 on 2 is 2. So we have x plus 2 and x plus 3, which is the fully factorized form that we got from the decomposition method. It's just if you can fully factorize something and it turns into this quite nicely, it doesn't make sense to fully factorize it via completing the square because it's a longer approach. It's a more general approach. So if you can factorize via decomposition, but completing the square is definitely useful for finding that turning point formula. Okay, so have a go at trying to factorize this quadratic equation using completing the square. So pause the video here and I'll come back in a few seconds. Okay, so hopefully you had a chance to answer this. The first thing I'm going to do is write down what my b value is, what my b on 2 value is, and what my b on 2 all squared value is. So b is -4, so that negative is associated with the x and the 4. So -4 is the coefficient there. B on 2 is -4 on 2, so -4 on 2, -2. And then b on 2 squared, so the negative times by a negative is going to disappear, giving us a +4. Now we want to add and subtract this b on 2 squared term. So we're going to have x squared minus 4x plus 4 minus 4 minus 7. These first three terms are going to combine to give us x plus b on 2. So x plus b on 2. So that b on 2 is actually a negative value. So we're going to have -2 there. Squared. And then we have -4 minus 7 left over. These are just going to add to give us -11. So x minus 2 squared minus 11. And that is the turning point form done via completing the square. Okay, let's do one more of these. So I've got another quadratic equation. Can you please turn this into the turning point form via completing the square? And then after you do that, I'll get you to fully factorize it. But initially, can you just create that turning point form via completing the square? All right, pause the video here and I'll come back in a few seconds. Okay, hopefully you had a chance to have a go at that. Now, when I was going over the completing the square method, I let my a value equal to 1 because when it's not equal to 1, the math actually gets quite hard. So you would initially factorize out this 6 outside of everything. So whatever coefficient's out the front, you'd factorize it out. And it just so happens that in this particular case, everything is divisible by 6. Otherwise, you would end up with a fraction. So we do that as the first step. So 6, we have x squared plus 6x minus 5. If that wasn't your first step, just pause the video here and then have another go at completing the square on this. Otherwise, I'll continue now. So the next step is to label what my b value is. So b value is +6. B on 2 is 3. B on 2 squared is 9. So I'm adding and subtracting 9 to this middle section of the equation. So 6x squared plus 6x plus 9 minus 9 minus 5. So I had everything the same as the previous line, except I'm adding and subtracting that b on 2 squared. Now, these first three terms are going to factorize into x plus b on 2. So 6x plus 3. So b on 2 is positive 3 in this case. Squared minus 9 minus 5. And so these are going to add to minus 14 because you've got a negative number and you're making it more negative. Okay, so we're at this point here where it's almost in the turning point form, except we have a 6 out the front that is a common factor to everything. Now, at this point here, you would take it in two different directions. You could finish this off by fully factorizing it, or you could expand this 6 into the equation to put it into the turning point form. So because the original question that I posed to you asked it for the turning point form, let's put this 6 in. So 6 comes in to just outside the first set of brackets, x plus 3. Because the brackets are squared, we can't actually bring it in without expanding that squared term. Because x plus 3 all squared is not the same as 6x plus 18 squared. So we then have 6 times by 14. So minus 6 times by 10 is 60. 6 fours are 24. So minus 84. So this is the turning point form with negative 3 and negative 84 being the turning point. But then if we want to find where it crosses the x-axis, we need to fully factorize this. So have a go at factorizing this question completely. So pause the video here and I'll come back in a few seconds to show you my working. Okay, hopefully you're able to get to the correct answer, but let's see what I would have done for this question. So it's of the form a squared minus b squared. So if we have a effectively being x plus 3, so x plus 3, and then if this is already b squared, then b is going to be the square root of this. So plus square root of 14. I'm going to have x plus 3 minus the square root of 14. And now that is our fully factorized form. So if, for instance, if this was equal to y, then our x, this graph would cross our x-axis when x plus 3 plus square root 14 is equal to 0. And it crosses the x-axis when x plus 3 minus square root 14 is equal to 0. So rearranging these equations, we're going to have x equal to negative 3 minus square root 14 and x equal to negative 3 plus square root 14. So plugging these into your calculator just to see what the numbers actually are in decimal form, we have negative 6.74 and 0.74. So if I was to jump on over to Desmos, putting this equation into Desmos, I can see that, yep, I'm getting negative 6.74, I'm getting 0.74, and then scrolling down to the turning point, I'm getting negative 3, negative 84. So again, the two different forms can tell me certain features within a graph. So in those two forms, I'll be able to plot out this graph. And then if I really wanted to, I would also sub in x equal to 0 in the original equation to find where it intercepts that y-axis. So it looks like it's intercepting the y-axis at negative 30. We see that the original equation, when you sub x equal to 0, you'd get negative 30 left over. So that would be, again, where it intercepts the y-axis.